If you drop a metal ball into a maze of pegs, its exact path is entirely unpredictable. It zigs and zags at random. But if you drop 1,000 balls through that same maze, a startling regularity emerges. They accumulate at the bottom to form a predictable bell-shaped curve. This diagram shows Galton's quinquunx. He used the accumulation of balls on the left to model genetic inheritance. But if you stack a second array of pegs below the first, like the middle panel here, the curve spreads out, creating a wider, flatter distribution at the bottom. If human traits like height were actually passed down this way, each new generation would become more physically extreme than the last. After a few centuries of this compounding variation, our population would stretch to extremes. We would have 9-foot giants walking alongside 2-foot adults. Because that doesn't happen, something else has to be going on. Galton knew the distribution of human height stays relatively stable over time. He spent 8 years obsessed with finding the physical, causal law of nature that kept the population from expanding endlessly outward. He updated his mechanical board to solve the problem. As shown on the right side of this illustration, he installed a row of rigid, slanted chutes between the two generations to force the outward drifting balls back toward the center. To Galton, these wooden funnels were a direct analogy for a hidden biological force. He called this force reversion, believing nature constantly and actively pulled extreme physical traits back toward mediocrity. He compared it directly to Hooke's law in physics, describing it like a stretched spring that naturally returns to its equilibrium resting length. Galton presented these chutes as a literal, physical process of cause and effect. He was mistaken, but his error forced science to abandon the search for physical causes and turn towards something else entirely. To see where his physical model failed, we have to look at the real-world measurements Galton collected, specifically comparing the heights of hundreds of fathers against the heights of their adult sons. This scatter plot maps those real-world measurements, forming an elliptical cluster of data points. If you isolate a vertical slice of tall 72-inch fathers, their sons are also tall, but as the black star shows, their average height drops down to 71 inches. Galton had stumbled onto the statistical concept of regression to the mean. Extreme observations are usually followed by more moderate ones. There are no physical chutes pulling these sons downward. The reality is that extreme traits require a combination of underlying genetics and luck. A father passes down his genetic baseline, but cannot pass down the random transitory luck that pushed his own height to the extreme edge. Without that inherited luck, the next generation naturally settles closer to the average. This statistical phenomenon is what keeps the bell curve of human height stable over time. That observation alone was interesting, but the realization that forced Galton to leave cause and effect behind is that the data works in reverse. Look at the horizontal slice of the 71-inch sons. If you trace back to their fathers, the fathers regress to the mean as well. The white star shows them averaging a shorter 70 inches. This discovery creates a strict causal impossibility. There is no biological mechanism where a son's extreme height can physically reach back in time and cause his father to be shorter. This geometric diagram maps Galton's breakthrough. Recognizing the relationship was perfectly symmetrical, he mapped its tangencies and invented a new mathematical concept, correlation. It provided an objective way to measure how strongly two variables predict each other, while remaining totally agnostic to what causes what. The mathematical legacy of this work is the correlation coefficient, a universal metric that scores the strength of a relationship on a simple scale without needing to identify a physical mechanism. In his search to find the physical cause of heredity, Galton accidentally discovered a mathematical lens where cause and effect simply do not matter. This mathematical shift was inherited by Carl Pearson, Galton's zealous disciple, who viewed correlation as a philosophical revolution. Pearson argued that the universe is just a collection of human observations, and since we can only ever observe patterns and correlations, the idea of an underlying objective cause is an unscientific myth. With this ideology, Pearson built a statistical empire at University College London, demanding strict loyalty to his data-only view of the world. He drove out any scientist who dared to use causal explanations in their research, treating causality as a slippery, outdated prejudice. His focus on pure data led him to combine measurements of male and female skulls from the Paris catacombs, proving that simply aggregating different populations creates spurious, meaningless correlations. Pearson successfully reduced all of science to contingency tables. If a relationship couldn't be proven with strictly symmetrical data, it wasn't allowed to exist in his laboratory. Galton's original quincunx experiment led to a result he never intended. A quest to discover the biological machinery of life produced a mathematical formula so elegant that it convinced the scientific establishment to stop looking for machinery altogether. For over a century, statistics became a model-blind data reduction enterprise. The discipline became efficient at calculating exactly what happened in a dataset, but it was practically forbidden from asking why. These causal diagrams compare the two worldviews. On the top is Galton's flawed mechanical board, where luck accumulates. On the bottom is the actual genetic reality, where only talent is passed down, and chance factors reset with every generation. To truly understand the world, we have to move beyond Pearson's pure data obsession. We have to learn how to put the physical chutes of cause and effect back into our mathematical models.